In this lecture, we're going to conclude our initial unit on linear regression, and the focus in this lecture will be on the effects of unusual data on the regression output. But we begin by a review of the linear regression function from a graphical perspective. And in this particular scatter plot, what we're looking at is the relationship between blood pressure, and this is systolic blood pressure, and age in a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 individuals represented by the circles. And of course, we have our regression line that has a positive slope. So this is a direct relationship. As age increases, we see a tendency for blood pressure, systolic blood pressure, to be higher. And what we have here illustrated in this circle here is the raw score from one participant, but that's the actual observed data, whereas the line is the best fit line, the one that minimizes the sum of squares, hence the term least squares. And the line represents the average value at that particular x value, and the distance between the raw data, the raw point, and the line is our residual, and that measures the magnitude of the error in the prediction. And you can see that it's not going to be consistent. So we have different residuals across the full spectrum. And what the overall standard error of the estimate that was touched on slide number 16 points to is an average deviation from the predicted value. Now, in this particular scenario, here we see an expected degree of scatter around the line of best fit. But what happens if we encounter what's called unusual data? And so in this scenario here we have a number of scores, paired scores on X and Y, and A, B, and C represents some rather unusual data points. But if you just take a quick visual scan of our data set here, it's going to be hard to detect data that might seem unusual. And so we're going to define unusual data as a data point far from the majority of the data, or what might appear to be the major cluster of data. And there are two types of unusual data. The first are referred to as outliers. And the outlier is an unusual data point of the criterion variable or the outcome variable. And so these are data that are indicated by a large vertical deviation away from the main cluster of data. The second type of unusual data point is the leverage point. And the leverage point is specific to the predictor variable, or a value that has a large horizontal deviation. It's important to note that data in our database, in our database here, or on a scatter plot, can be both an outlier and a leverage point. And so what's really important to understand is how these unusual data can affect the correlation and regression analysis. And when researchers encounter these unusual data, the first question is to ask, why is it unusual? Is it because of some blunder that was committed when entering the data into the computer? Was there an issue with including that data? Was it an issue of research design? So all of these items must be addressed in order to determine why that particular point is unusual. One last bullet item here is that unusual data are typically more influential when we have relatively small samples. So on the next 5 slides, what we're going to do is I'm going to generate scatter plots of these data with or without the unusual data labeled as A, B, and C. So if we generate a scatter plot of all the data on slide 19, including A, B, C, and I use Microsoft Excel to generate this scatter plot. Here we have a line of best fit, fit by Microsoft Excel, and it generates our regression equation and our R-squared value. Note that our regression equation has two parameters in here. It has a slope and the y-intercept, or the value of y when x equals 0. And so here we're just taking a visual determination of our main cluster of data. There's an upward trend definitely as we go from left to right along the x-axis. So do we move vertically. And our regression equation here and our key statistic, our R-squared value, describes the magnitude of the effects not produced just by the central cluster here, but by all the data. And so to interpret our main statistic, which is our coefficient of determination, our R-squared value, as illustrated on a previous lecture, we multiply our R-squared by 100%, or just simply move the decimal place over twice, and we would conclude that 19.2% of the variability along the y-axis, if you look at all the data points, they're not all at the same y, so they vary along the y-axis, is accounted for by the variability in the data along the x-axis. Only 19% is accounted for by the change in the x-axis. That would leave the balance of this approximately 80%, 81%, is accounted for by factors not addressed in the study. For all intents and purposes, it's randomness in the data that accounts for most of the variability. And how are the unusual data points potentially influential here? We start with this first data point here. And what we see is in the vertical direction, this data point is clearly a distance from the central cluster. And so because it's vertically deviated quite a bit, we refer to that as an outlier. If we take a look at this one over here down to the right, that's our leverage point. And so the leverage point is a large horizontal deviation, but if you follow this point over to the y-axis, you can see that it still sits within the cluster of the y data. Likewise, the outlier along its x value still sits within, actually right in the middle of the main cluster of data. And at the top right-hand corner, here we have a data point that is both an outlier and a leverage point. So the next few slides, we're going to generate scatter plots to show how these data points can affect the overall regression analysis. So when we include all of the data, we have a very low level of predictability. So on this slide, what we're seeing here, we have that central cluster highlighted on slide 19. So the unusual data points A, B, and C were not included in this scatter plot. And we see here that our coefficient of determination is just shy of 85%. Yes, we have scatter about the line of best fit, but the variability of our data in the y direction, or along the y-axis here, 85% of that variability, or almost 85%, is accounted for or explained by the variability along the x-axis. So now we have a rather strong degree of predictability. On this slide, what you see here is the outlier. So I'm going to include one unusual data point at a time. So if we include just the outlier, that's our A value, or our the paired data labeled A. Here we see that the predictability is considered to be low at almost 38%. So the outlier considerably reduced the magnitude of our predictability. So we dropped from 85% or close to 85% down to 38%. The inclusion of B, remember that B was both an outlier and a leverage point. And if we take a look at, let's just make sure we indicate this, that B has a large vertical deviation and also has a large simultaneously X or horizontal deviation. And this is the largest value of predictability that we actually have here. Unusual data do not always necessarily reduce the predictability of between the two variables in your data set. Here we actually see an improvement in the strength of the prediction up to almost 93%. That's a large improvement from almost 85% when the unusual data were not included. All three were not included. And finally here, we have the inclusion of our leverage point. And so our leverage point along its Y value still sits within that cluster, but its X value is quite large. And so the leverage point, as you can see, has the largest effect on reducing the predictability. Now we're down to 8.62% in accounting for the variability of our Y variable by the variability of our X variable. So if we place all these on this one table here to summarize the different statistics generated depending upon what data are included, what we clearly see here, let me just pull this up here, when we only included the leverage point had the most pronounced effect. So whenever you're examining correlation and regression data, always make note of your sample size. And so if we had all of the data included, we had a total sample size of 21, but if you're not including data, you can see how these sample sizes are different. And so the most pronounced effect, and I'm making this conclusion here by the R-squared value. So here we see the largest R-squared value of close to 93% in terms of predictability occurred when we only included the B unusual data, which was both an outlier and a leverage. The lowest was when we only included the leverage point in our analysis. And so the other notable feature here is in the slope. And so the very low predictability here of 8.62% on the R-squared value is reflected in the lowest slope. So with a slope of 0.1428, this is approaching a horizontal line of best fit, as opposed to the other slopes, which are quite a bit different than the 0.1428. It's only when A, B, and C all were included, we can see that we have a fairly low slope, but not nearly as low as when we had that leverage point. So the leverage point has the effect of tilting the regression line, and by tilting the regression line, it had the tendency of increasing the y-intercept. And so the increase in the y-intercept came by way of the rotation of the line comparably to the other conditions, to the other analyses, not necessarily by vertically shifting the line. So rotating the line of best fit will have a rather pronounced effect on the y-intercept of our data. So this ends our final video on our regression analysis unit.